Problems on LCR. Let me brief you on LCR again. It is the series configuration. LCR is in series supplied with AC source. That AC source has the voltage V and the current I. Since voltage and current are constantly changing in magnitude and direction, we need to take it their mean values. The appropriate mean values are RMS values. The RMS value, it is RMS value of the AC source, RMS value of the current, AC current. These RMS values are related to the peak values, their corresponding peak values. That is, I RMS equals the peak value of the current divided by root 2. The same way, the voltage equals the peak value divided by root 2. The relationship between the peak value and the mean value. In this AC circuit, this is the equation. Equation is Ohm's law of the circuit. Here the voltage equals current into resistance. Z is resistance of the circuit. It is also called as impedance of LCR, the total resistance by the LCR circuit. This impedance is given by this equation. Since the total resistance is actually, if the source is DC, the total resistance of all the components in series are sum of all the resistances. But it is not DC, it is a source of AC. If that is the case, so we have to apply this summation. That is the resistance of the resistor, and this is a difference between the resistance of these two components. That is also called as reactances. Delta X whole square. This delta X is difference between the resistance of the two components XC and XL. There are three possibilities. Here XC is greater than XL. The difference is this. In this case, capacitance dominates over inductance. If that is the case, it is called as capacitive circuit. The second possibility, if XL is greater than XC, the difference is this, dx, delta X is this. In that case, inductance, that is L dominates over C. It is called as inductive circuit. And the other possibility is delta X equals 0. Delta X equals 0 if these two values are equal. Then the Z equals R. It is known as a state of resonance. Similarly, we can apply this to the voltage. In case of DC source, the sum of the voltage drops at the different components equals the total voltage what is applied. But in AC source, it is not that case. You have to take this summation. That is voltage drop at the resistor plus difference in voltage drops at these two components delta L, delta V whole square. This summation is this total source or total voltage in the circuit. So we can apply the same case here. The difference is this. If this is greater than this, it is called as capacitive circuit. If this is greater than this, it is called as inductive circuit. If this is equal to 0, VL equals VS, it is known as resonance. Similar case can be applied to voltage as well as resistances. And the resistances are defined. I will give the equation again. This is defined by this equation. This is defined by this equation. And these two resistances are variable. Whereas this resistance is always constant. It is not depending on the frequency of the AC. F stands for frequency of the AC source. And this is how they are related to frequency as well as their specific values L and C. And at resonance condition, at resonance state, so this becomes F naught. Frequency, resonance frequency is related to the values of L and C. And in this equation, this VR is given by Ohm's law again. Voltage drop at this is equal to current into resistance. So the current is flowing through all the components remain same in series. Same current is flowing, but it differs only in resistances as well as voltage drop across the components. So this is I into current. The current remains same in all the voltage drops. Current remains same passing through, and the corresponding resistances are, this is R for resistor, this is the resistance of the capacitance, resistance of the inductor, and these are the definitions of voltage drops. And in case of LCR, there is a phase difference, angle of phase difference between the current and the voltage. The phase difference is given by tan inverse of difference in this delta x divided by R. If XC is greater than XL, in that case, the current leads voltage in the circuit. If XC is greater than XL. Suppose if XL is greater than XC, voltage will lead the current in the circuit. This ratio delta x divided by R is tan inverse of that is the phase angle difference between the current and voltage. In this case, current leads the voltage. In this case, voltage leads the current. And this is cos phi. What is the cos phi is known as, it is the power factor of LCR. The power factor of LCR, the value varies between 0 and 1. In between them, it becomes a fraction, power factor cos phi. So we have to remember all these equations or formulae on the LCR circuit. All these formulae are applicable to LCR, explained in brief. Let me pass on to the problem, the solution of the problem. The first problem is, this is the one. Problem is not written. The data of the problem I have noted down. I will read the problem. The LCR circuit, it is in series. The LCR is in series. Given the values of L, R, that is that is self-inductance, resistance, and AC source, voltage source, and frequency of the AC source. All these data are given and asked us to calculate capacitance of the capacitor which can drive the circuit into resonance. What capacitance value required to drive the LCR circuit of this data into resonance state? And the second problem, second question is, you have to calculate what would be the voltage drop at the inductor. Voltage drop at the inductor at resonance. Let us go for solution. During solving this problem, we must know what is the value of 2 pi. We often come across this 2 pi value. It is given by 6.283. That is 2 into 22 by 7. This is the value we get. For the calculation of C into resonance, the equation required or suitable is this equation. The equation of resonance frequency, that is the one I have selected from the list of the formulae. F naught. F naught equals, I am given all these values L and F naught. We can find out what is the value of C. It requires rearrangement of the equation, squaring both sides and taking C equals, we get this equation. 1 divided by this into 1 square into L. Substitute for these values. This value is this value, and value of F naught is given as 50 hertz, and value of L is 0.5 Henry. Simplified, take the inverse of it, we get this value. This value is capacitance of the capacitor, which can drive or which can make this frequency as a resonant frequency. We can make this frequency 50 hertz as a resonant frequency. This capacitance value required for that one. Second one, calculation of voltage drop at the inductance. So voltage drop is equal to current into resistance. Resistance of the inductor is XL, and the current value is not given. You have to substitute for I, V divided by Z. That is voltage in the circuit, voltage supplied to the circuit divided by the total resistance of the circuit, Z. Mentioned at resonance, Z equals R. R value is given. And XL value is known that 25FL. Equation for XL is 25FL. All these values are given. Substitute for them and simplify. Value of V, value of Z is taken as R, and value of 2 pi is this one. F equals this, L equals 0.5. Simplify, we get this value. This is in voltage. Voltage drop at the inductance. So these are the values we have calculated for this data of the problem. Second problem, again the problem is not written. I have listed out the data of the problem. It is again LCR is in series circuit, and the corresponding values of resistance of the resistor is given, and self-inductance of the inductor is given. It is milli Henry, 10 to the power of minus 3 Henry. And the capacitance is 22 microfarad. Voltage is this value, and frequency of the AC source is this value, and you have to calculate, ask us to calculate what is the current, AC current flowing through the circuit, and what is the phase angle difference between the current and voltage in the circuit, and the power factor of the LCR. The equation suitable for this is I. Ohm's law. Current in the circuit equals voltage divided by the resistance. The resistance is impedance of LCR. This value is given, but this value is not given directly. Instead, the values of L, values of F are given. Calculate the Z is equal to this value. The values R is given. Delta X value you have to calculate. So for that you have to find out what is the value of it. The equation for XL is the equation. Substitute for these values. This is 150 into 100 into 10 to the power of minus 3. That is 100 milli. Simplify, you get this. This is in ohms. XL is in ohms. Similarly, calculate the value of XC. The equation for this is the one. Substitute for these values F and C. C is microfarad. Substitute for micro because farad in SI. 10 to the power of minus 6. And simplify, multiply, take the inverse of this, you get this value. It is again resistance, that is ohm. Since they are resistance values, ohm values. Then find the delta X value. Higher value minus lower value. This is delta X is this. This is capacitive reactance. Here the capacitive is current leads the voltage. In this case, current leads the voltage. With these values, calculate the value of Z. Given the value of R. This is what you have calculated. Take the whole square. And you have to simplify inside, then take the root of it, you get this value. It is again in ohm. This is resistance 163.8. Then take this equation, put the values of V and Z, and simplify, you get this value. This value is in amperes. 1.343 amperes AC current in this circuit. That is what it is asked us to calculate. High value we have calculated. Then you go for calculation of pi. Pi equals, we have to take this equation, tan inverse of this. Difference in this is higher value minus lower value. This is higher and lower value. Difference is this, already you have calculated difference. R is value is this. This value equals 3.12. Tan inverse of 3.12 is 72.2 in degrees. Tan inverse of this is the one in degrees. 72.2 degree is the phase angle difference between current and voltage. Here current leads to voltage, phase angle. So now it is calculated, and the final calculation is cos of pi, power factor. Take the cos of this value and read this cos directly in the logarithm table. The value of this value is 0.3052. This 0.3052 is the power factor, fractional value, the power factor of LCR. As you know, the power factor of LCR gives us the idea of what magnitude of power get dissipated through R in the LCR circuit. Maximum power or minimum power. It depends on the value of this. Value of this. It is called as power factor. Decide what amount of power will be dissipated. So with this we have completed this. So let us continue with some more problems. Only thing we have to remember, all these formulae about the LCR circuit in series. So whenever the LCR circuit comes in the picture, so these formulae, that is the equations which are applicable to this LCR should be remembered. So with this we have just completed this. Thank you very much.